Hey, welcome back to Math with Patrick. Today's November 24th, and we're solving problem 328 from the Daily Epsilon calendar. And we need to find the area of this blue triangle right over here. The area is x, and x is supposed to be 24 today because it matches today's date. So we have a square, and I know it's a square because we have these double tick marks saying that these two sides are the same length. And then we have enough right angles in the diagram to say that all four of these are right angles. Also, we have this point right here that bisects this left side. It just cuts it in half. And then this diagonal becomes the hypotenuse of this bottom left triangle, and then also the longer leg of this middle triangle. We also have another line right here that seems to just kind of go up-ish to the top. I'm not exactly sure how far across this square it is. I mean, it kind of looks like it's a quarter of the way there, but I'm not quite sure yet. This comes at a a 90-degree angle, not 45. And then we have yet another right triangle. It's kind of like we have this right triangle pattern where the long leg turns into or the hypotenuse turns into the long leg of the next one. And then finally, once we've gotten to this triangle, we can connect the top, and it's this skinny triangle on the right side that we need to find the area of. Now, it would be convenient if we had some kind of height for this triangle. Let's just say like right here. Because we already have the base, which is this length over here. And the height and the base need to be perpendicular for our standard area formula for triangles to work. Now, fortunately, they are. There is going to be some kind of 90-degree angle right here, but finding this height length isn't that easy. Let's write our formula at least. Area is 1/2 base, and then hopefully we get some kind of height value to stick in right here. So let's use the diagram to figure out how we can get this height value. Well, if this and this are half of the 8√3, then we just have 4√3 in either spot. And then I guess we could use the Pythagorean theorem to learn more about this length. And I'm also going to rely on what I know about proportional triangles to help me out here, because I'd rather just do the Pythagorean theorem on a triangle like this, where I'm just choosing easier values that are still double or half of each other. And this will help me learn some kind of scale factors that let me move around these values more quickly. I'd rather not Pythagorean theorem bigger numbers if I don't have to. The Pythagorean theorem here would just say that 1 squared plus 2 squared is equal to the hypotenuse squared. And that just tells me that the hypotenuse here is √5. And this helps me with my diagram because I know that I could just multiply by √5 to go from the shorter leg to the hypotenuse. So this will be 4√15. Now, I'm a little stuck at this point just because I don't have all the information that I want from this middle triangle. I really want this leg so that I can do the Pythagorean theorem again to get the hypotenuse. And fortunately, I think this little triangle is going to help out. I would like to claim that the little triangle right here is actually similar or proportional to this big triangle right here. And I'm color coding the angles just to kind of show what angles correspond to which other ones. And my argument here actually comes from this triangle down here, I think, because I'm noticing on the left side of the diagram, I have 3 angles that make up 180 degrees. One of the angles is 90 degrees, so therefore the other 2 must be complementary or add up to 90. And so this orange and this blue angle are going to add up to 90. And then because I'm living in a right triangle down here, I know that these angles are also going to add up to 90. And so this orange angle is the same as that one, and actually this one, just based on the diagram. And then if this is an orange angle and we're in another right triangle, that has to be a blue angle, or complementary ones, essentially. And the reason why this is important is that I know that this triangle down here is proportional to my 1, 2, and √5 triangle. So proving that this is now similar or proportional to those, I can just quickly learn about the proportions here and apply them to my diagram. It looks like I have information about the longer leg. So if I divide by 2, I get the shorter leg. And then like before, if I multiply by root 5, I'll get the hypotenuse. So here I don't really need to think about the Pythagorean theorem too much. I'm just working with proportions. So this is me dividing by 2, and this is me multiplying by root 5. And this triangle also is similar to all the other ones we've talked about. So I could just multiply this value by root 5 to get the hypotenuse. Now I think it would be nice to then kind of break apart root 15 as root 5 times root 3 again, just to show that both of my root 5s multiply together to get 5. 5 times 2 is 10, and then I still have this root 3 off to the side. And as you can kind of tell, our knowledge of this diagram is kind of getting closer and closer to this h value, so that feels good. I can use proportions again. We have the same kind of right triangle here. It's similar to all the other ones, so I can divide by 2 to get this length. And you know what? I think I'm going to break my pattern just a little bit. I'm noticing here that if I figure out this kind of base of this right triangle right here, then I will actually get to know this height, right? Because I have information about this 2 root 3. And if I know this length, then I can figure out this one because I know the whole length is just 8 root 3. So I want to take a look at this triangle right here. I'd really like to know more information about its sides. And I think what I can do is actually use this diagonal right here. This diagonal, or I guess this longer leg of this triangle or the hypotenuse of this triangle, I mean, everything's overlapping. This side right here is perpendicular to this one right here. That means the slope of this one is going to be an opposite reciprocal of the slope up there. And I can kind of carefully look at the tick marks in my square here. And I notice that I'm moving 1, 2, 3 units to the left, and then 1, 2, 3, 4 units up. Each of these units is a distance of 2 root 3. So the slope here is going to be rise over run, but then I guess the rise is going down, so it's a negative 4/3. That does mean that the slope of this blue diagonal, this hypotenuse up here, is going to be the opposite reciprocal. So that's going to remove the negative sign and then flip to get 3/4. So the slope of that blue line is 3/4. That must mean that this side and this side have a ratio of 3/4. Now, it's not just exactly 3 and 4. Rather, it could be 3 times something and 4 times something, and they'd still have the same ratio of 3/4. But fortunately, I can apply yet another Pythagorean theorem to this and figure out what this a value should be. Or I could think back to proportional triangles. I can think of my 3, 4, 5 triangle, and I can notice that I should just multiply by root 3 on all 3 sides to get back to this triangle that I'm studying currently in the diagram. This shows me that this a value is just root 3. Or in other words, this golden length that I'll highlight right down here, this one is 4 root 3. And here I'm basically done. This 2 root 3 goes 1/4 of the way across my square, and this 4 root 3 goes halfway across a square. Therefore, this is another quarter of my square, at least the side length right here, and that's going to be another 2 root 3. This length down here is also just the same height as the blue triangle that we're trying to find, but I guess we can kind of see that either this side or this side, whichever one I look at, this height is going to be 2 root 3. And here we're basically done. Now we just need to use our area formula. I'm going to multiply those root 3's together. I'm going to cancel the 1/2 with the 2. And so we're just left with 3 times 8, which is 24. So that's my solution for this problem. Maybe there's a quicker way that, doesn't involve as many steps, but I couldn't find one. So I used slope, I used perpendicular lines, I used right triangles and proportions and the Pythagorean theorem to figure out that yes, indeed, the area of that triangle is 24. So I'm all done for today. Thanks for watching, and I'll see you tomorrow.